Last time we talked about isomorphism of graphs, and this was a way for us to say that two graphs are kind of the same. And before, if we just had sameness meaning equality, that would mean that, well, equal pairs of sets, right? A vertex set and an edge set in one graph should be equal to the vertex set and the edge set in the other graph. And that didn't really give us enough flexibility to take two graphs which kind of look structurally the same and say in what sense they're actually the same. But isomorphism gives us exactly this. And if you recall, the definition says that there's a bijection between the vertex sets where an edge in one graph maps to an edge in the other graph. And in the second graph, any edge in the second graph has to come from an edge in the first graph. So we said uv is in the first graph, let's call it g, if and only if f of u, f of v is in the second graph, h. And this is pretty much the standard definition. But there's another way to think about it in terms of something slightly more general, and I think slightly more useful. And that's in terms of something which is like an isomorphism, but a little bit simpler, and it's called a homomorphism. So that's going to be our topic for today. So here, like I said, last time we talked about isomorphism as a function on the vertices with some special properties. That was, it maps edges to edges and vice versa. And today we're going to get an equivalent definition, and we're going to build it up from this definition that we had for sets. Remember, for sets, we had equality of sets and isomorphism of sets. Well, we're going to make it so isomorphism of graphs looks almost exactly like isomorphism for sets, and here's how. So remember the definition for sets, if x and y are sets, we said that they're isomorphic if we had this pair of functions, right? And let's remember what they had to be. It had to be that f was a function, say, from x to y, and g was a function from y back to x. And it should be the case that if I compose them, I get just the identity function. So g composed with f was the identity on x, and f composed with g is the identity on y. And let's just double check that that makes sense. So if I'm in y and I apply g and then f, I get back to y, and it should actually be an identity. And similarly, if I'm in x and I apply f and then g, you'll get used to the fact that these look reversed in the, right? They're written in the reverse order of how you apply them. But that's just how we parse functions. And so if you have these two functions and they satisfy these two conditions, then we say that the sets are isomorphic. And we're going to want the same kind of thing for graphs. So I want, really I'm going to call it the same definition for graphs. And let's just be clear about this. I'm going to need something like a function on graphs. Because this is in terms of functions. So we need something to fill that role of functions. And that's going to be a homomorphism. And what we'll get in the end is actually the definition for isomorphism of graphs will be exactly this if we were to just replace the word sets here with graphs. So this is, in some sense, the template for what we're going to mean by isomorphism. So let's build it up. So here is a graph homomorphism. The graph homomorphism is going to play the role of the function for graphs. Okay, so what does it mean? It's going to be a mapping, and we're going to write it just like we would write a function, right, with an arrow. So from a graph G to a graph H, it's going to be a pair of functions. Think of it as a function on vertices and a function on edges. And these look like you hope they would look like. So for instance, this function on the vertices, fv, is going to just map the vertices of G into the vertices of H. And the function on the edges, well, is going to be a function from the edges of G to the edges of H. And we have this other condition, which is that this function on the edges has to correspond in some way to the function on the vertices. And we write that as follows. It says that fe of an edge uv has to equal this pair fv of u, fv of little v. Right. So in fact, I don't actually have a lot of choice once the function on the vertices is fixed, the function on the edges is also fixed. It's given by just this. And I've written this as a string, but of course you should also think of this as a pair. It looks a lot like the definition for isomorphism that we've seen in some ways, because you see we have a function on vertices that induces a function on the edges, and it really has to map edges to edges. The difference is it only has to go one way. So let me just draw this a slightly different way for you. So if I have my graph G, and I have a homomorphism from G to H, well, G was equal to a pair, VG, EG, and this was equal to VH, EH, a vertex set and edge set for each. And so what I had was this function FV here and FE here. So just like we separate out the graph into two parts, we can separate the homomorphism out into two parts. And it's not enough to just have a function on the vertices and a function on the edges. They also have to satisfy that third condition, which I'll write it one more time because it's so important. Right, for, let's call it UW, so I don't have to say V so many times. It should be the pair FV of U, FV of W. So in pictures, here's a graph G and a graph H. Now, you should be able to see immediately that these are not isomorphic. Right? There's no way to have a bijection between the vertex sets because this one has 3 vertices over here, and there's 4 vertices over here. On the other hand, I can still have a function that maps the vertices of G to the vertices of H. And I've given one here. So I'm going to take the function that maps A to 1, B to 0, and C to 3. And again, I'm using this notation. Remember, this is maps to, not just the 2. So this is telling me really all the mappings. And this mapping on vertices induces this mapping on edges. So the edge AB over here maps to 1, 0 over here. The edge BC maps to 0, 3 over here. Okay, so the image of this homomorphism, you could think of it as this subgraph over here. So there's this graph G kind of gets mapped into H over here. We would check that it is in fact a homomorphism. So it's certainly a function on vertices. I define it that way. I have a function on edges, right? Every edge here maps to something over here, which is in fact an edge. Right? Since each of these are edges in H, it's a function on edges as well. And we check this third condition, that each edge is mapped to the ends that you get mapped to by f of v. So FV of A was 1, FV of B was 0, and so AB maps to 1, 0. Similarly, BC is 0, 3. In fact, we just, in some sense, defined it that way. So it satisfies the 3 conditions needed to be a homomorphism. I could have picked other functions. Let's see. For instance, imagine I did the following. I say A, B, and C are going to map to, let's pick 3 other vertices. Let's pick 2, 3, and 0. That would mean that FE should map to, well, it should map AB and BC to, well, AB will go to 2, 3, and BC will go to 3, 0, which is the same as 0, 3 here. But if you look, you'll notice that 2, 3, this edge right here, is not actually an edge in H. So if I have something in here maps to something that's not in H, then this FE is not actually a function from the edges of G to the edges of H. So this, in fact, is not a homomorphism. Right? It fails to be a homomorphism for that reason. Now, you might fail in other ways. Let me try this one. What if I mapped A, B, C to 1, 1, 0? Now, again, this is a valid function from the vertex set of G to the vertex set of H. If I look at what happens to the edges, I've got AB and BC will map to, well, AB will map to 1, 1. BC will map to 1, 0. Now, 1, 0 is an edge in H. But 1, 1, right, this is the set 1, 1, which is really just a set with one element. There are no edges with only one element. This is not in EH. So this is also not in EH. And so again, neither of these would be valid homomorphisms. Even though they are functions on the vertex set, they don't have this property that the function on the edges is induced by the function on the vertices. Here's an example of something that is a homomorphism, and here's two examples of things which are not homomorphisms. Now, in this case, it looks like when I take this valid homomorphism, it maps it to something that looks isomorphic to G. Now, that doesn't always happen. In fact, you can come up with examples where the image of the homomorphism does not look like the domain of the homomorphism. In fact, it's not even going to be isomorphic. And let's see how that happens. So, same two graphs. And in this case, I've given a different function on vertices. So here it is. A is going to map to 1, B is going to map to 2, and C will map back to 1. Okay, so if you were to look at where this goes, it goes from 1 to 2 to 1. So somehow covers this edge twice. And so on the edges, A to B, AB maps to 1, 2, BC maps to 2, 1. These are in fact the same edge. So both edges of G map to the same edge in H. This is still a function. It's just not an injective function. So we can check that it satisfies the properties we want. Right? There are three properties necessary to be a homomorphism. One is that the function really is a mapping on the vertex sets. That is clearly true. Right? A, B, and C, I've got all the vertices here, and each one of them maps to a vertex in H. So let's check that one off. Good to go. Now, this function on edges, this is also a function, right? Because every element of the edge set of G maps to an element of the edge set of H. Good. And now we checked also that this coherence condition is satisfied. That is, the mapping of any edge is just whatever we get from mapping the vertices with FV. So in this case, I've got two possibilities, and we can see that they clearly work, right? Because AB, A maps to 1, B maps to 2, and it maps to 1, 2. BC, B maps to 2, C maps to 1, so it maps the edge to 1. For every edge, this is true, and so we've got all three properties needed to be a homomorphism, but it doesn't look isomorphic to the domain of this homomorphism. So you can do weirder things with a homomorphism. And it's clear in this case now that there's no inverse, even if you just restrict yourself to the image. Right? If you were to look at the pre-image of these functions, you'd see that this edge, for instance, maps to both edges. And this vertex actually maps to A and C in the pre-image. Okay, so this is what might seem like a more exotic kind of homomorphism, but it's pretty normal. It's just like with functions, where sometimes a function is not injective. This would be a homomorphism that's not injective. All right. Well, let's put this to work. So here's kind of one of the first standard theorems that you learn about homomorphisms, is that you can kind of characterize some graph properties in terms of whether or not a homomorphism exists. And so here's one of the best ones, right? If a graph is bipartite, remember bipartite graphs, the vertex set can be partitioned into two pieces where all the edges go from one piece to the other. So we'll call the two parts in the partition A and B. And so every edge has to go have one end in A, one end in B. The claim here is that a graph is bipartite if and only if there's some homomorphism from the graph into K2, which is, remember, that's the complete graph on two vertices. It just looks like two vertices and one edge. So there's two directions here because it's an if and only if. So first case, suppose we have this homomorphism from the graph into K2. Okay, so that homomorphism is a pair of functions. So on the vertex set, I've got this mapping from, I put G here, but this should be from the vertex set of G into 0 and 1. And so if I look at the preimage of 0, as all the vertices that map to 0, that's some subset of G. And then the rest of them must map to 1. So the preimage of 1, we'll call that B. All right, so this vertex set now of G has been partitioned into A and B, right? The preimage of 0 and the preimage of 1. We want to check that every edge goes from A to B, because this is saying that if we want to prove that G is bipartite, what we'll do is we'll just show what is the partition of the vertex set and show that every edge really does go across. Okay, so there's a couple ways we could do this. Suppose, for a contradiction, that some edge, UW, has both endpoints in, let's say it's in A. The proof will be the same for B. So suppose UW is an edge in G, and U and W are both in A, right? So that would make it no longer bipartite. But we can just check then that FE of UW, because we suppose we really do have a homomorphism here, FE of UW is equal to the pair FV of U, FV of W. And by definition, since they're in A, it means that they map by FV to 0. So this is equal to 0, 0, which is not in the edge set of K2. And so that would be a contradiction. Okay, so it can't be the case that both ends of any edge are in A, and the proof is similar for B. And so we get, in this case, if we have the homomorphism, then it must be bipartite. All the edges have to go from this A to this B. I'll draw a picture of this in a second, but intuitively it's saying that the graph G had two parts in it, and one part got mapped to 0 and the other part got mapped to 1. And this condition about being a homomorphism says that all the edges had to kind of land on this one edge, right, crossing between the two parts. So the other side of this is if the graph is bipartite, then you have this bipartition, and so we can use that to define the homomorphism. And it's what you would hope it would be. It's going to map each vertex to, well, 0 if it's in one part and 1 if it's in the other part. In fact, you could swap these two. It would be a separate homomorphism. Okay, so if we have this, I've told you where the vertices go, and now you would just have to check that when I define FE, right, remember FE is going to map UW to FV of U, FV of W. You want to check that this, in fact, really is a homomorphism. So if I define it this way, it must satisfy the third condition. We just have to check that it really is a function, right? There really is a function on edges. And that just means that we have to check that this is always an edge in K2 when there's only one edge. So that means that for every edge in the graph, it has to map to the edge 0, 1. Right, so we want to check that it's in the edge set of K2, which again is just a single edge. Right, and it's easy to see that if this was not the case, then the graph would not be bipartite. Every edge has to have one end in A and one end in B, and so every edge will map to a 0 and 1, or 1 and 0, which are the same edge. So F equals FV FE is the desired homomorphism. Okay, there's one case that I kind of left out here. Let me just put a little asterisk, and it's worth remembering that if G has no edges, then it is bipartite. We didn't work this out in detail, but it's really easy to see that you just leave one of the parts empty, and you still have the case that every edge goes across between the two parts. It just happened to be no edges. So this is the one trivial case that is not covered in this case. But also, if there are no edges, then it's also trivial to have a homomorphism between the two. All right. So now, given this definition of homomorphism, and we've got at least a little bit of practice with it, we can revisit the definition of isomorphism. Oh, this little part that got cut off here is redefining isomorphism of graphs. Okay, so now in this time, we're going to say that two graphs, G and H, are isomorphic if there exists homomorphisms from G to H and from H to G, so that when you compose them, you get the identity. Now, there's some missing pieces here. Right, so the condition is going to be that G compose F is the identity on G, and F compose G is the identity on H. But in order to make this statement, we need to say what we mean by identity and what we mean by composition. Right? These are things that we defined for functions, but we can define them just as well for homomorphisms. Right? So the identity homomorphism on a graph is just the identity function on its vertex set and the identity function on its edge set. Okay, so the graph is a vertex set and an edge set. These are sets, and so sets have identity functions, and so we can build up an identity homomorphism from the identity functions on these two things, and you can check that it satisfies the three conditions. That's a nice little exercise. Similarly, for composition, F composed with G is just going to be the function on the vertex sets composed with each other and the functions on the edge sets composed with each other. Okay, again, it's a very simple exercise. I encourage you to do it to check that composition of two homomorphisms is still a homomorphism, that it actually satisfies the definition of a homomorphism. Right, so if I have graphs A, B, and C connected by homomorphisms in this way. Oh, I probably should put them in the other order here. Let's do it like this. There's G, and there's F, right? That F composed with G maps A to C, and that is a valid homomorphism. Okay, and clearly I didn't write it down, but the type of the identity for G should map G to G. Oops. Right? It is a homomorphism from the graph to itself. In a way, it's perhaps the most obvious and natural one. All right, so let's check. I claimed that these definitions are equivalent. Let's just see what would be involved in checking that that's really true. So in both definitions, we have this function on vertices. So FV maps the vertex set of G to the vertex set of H. In both cases, it has to be a bijection. Maybe is that clear here? That it has to be a bijection because the composition of these two has to be equal to the identity, right? So that has to be true at the level of the vertex maps. Right? So I've got the function on the vertices has some inverse function which maps it back, and it should be equal to the identity, which means that it's a bijection, right? So bijections have this property that they have an inverse function where the composition gives you the identity. In both cases, I have this bijection, and now what I'll say is, okay, GV is just going to be that inverse of that bijection, and I define the homomorphisms, FV, FE, where FE is going to be, like you hope, it's going to be the thing that satisfies our third definition of a homomorphism. I'm just going to say wherever the vertices go, that's my new edge. And similarly for G, if I have an edge over here, it's going to map it to GVU, GVW. Now, once I've given you a function on vertices, I'm going to tell you what the function on edges is. The only thing you have to do to check that all the definitions are satisfied, to say that these really are homomorphisms, you check that these, in fact, always land as a edge in G. I'm sorry, in H, and this always lands as an edge in G. And you would then check also that that definition, the original definition we got for isomorphism, which said that an edge was an edge in G if and only if the FV of U, FV of W was an edge in H, that corresponds to these sort of same conditions that we put on a homomorphism. All right, so the definitions in terms of just a bijection on the vertices that maps edges to edges and vice versa, and the definition of isomorphism in terms of the existence of homomorphisms that compose to identity, that these two are equivalent. All right. So I promised you one picture. Let's just do one more so we get a feel for this. This claim that bipartite graphs are bipartite, I should say, if and only if they have some homomorphism to K2. And in this case, right, since it's bipartite, I've got the set A and the set B. It means that I map this to the first one, let's call it 0, this one to 1. All right, so this was FV of U was equal to 0 if U is in A, 1 if U is in B. Okay, so in pictures, that's what we have. So if there is any such mapping, right, all these edges, you see the edge has to land on this one edge here. And if there was an edge in here, it would get squashed. And edges can't be squashed to a single vertex in a homomorphism because we would violate this third property that, or actually the second property, that the induced function on the edges is actually a function. Okay, so that if I had an edge in here, I'm going to dot it in, it's not really there. If I took an edge here, this mapping on the vertex set would take this edge and map it to just one vertex, and therefore it would not be a function from edges to edges. And so just requiring it to be a proper function on edges is enough to guarantee this kind of property. So this is the picture version of the theorem that a graph is bipartite if and only if there exists a homomorphism from the graph to K2.